general engineering physics. A bunch of brave guys here. He's had a lot of research experience. He started in the summer of 2010 at Harvard. He worked with a group where they looked at adapted and digital holographic microscope for the tracking and following of Brownian particles. In the summer of 2011, he did some research in the summer at Princeton University where he looked at, developed an algorithm, worked with a group that developed an algorithm for phase reconstruction in digital holographic microscopy. Continued on in summer of 2012, back to Harvard University where he worked with a group where they were primarily concerned about optimizing GPU and the high-performance GPU cross-correlator for application to large radio telescope arrays. He has further experience in designing a rocket-powered grenade launcher simulator for testing radar equipment and has been a lab instructor for the last 3 years or so in Eastern Nazarene College. The title of his talk is Optimizing Cross-Correlation on Graphic Processing Units in Radio Astronomy with Gauss's Complex Multiplication Algorithm. Welcome, John Keller.
Last summer I worked at the Harvard Smithsonian Center for Astrophysics with Lincoln Greenhill on optimizing computational efficiency, etc. And this is an example of one of the radio telescope antennas we used. So the motivation for the project comes from figuring out what the universe looked like shortly after it began expanding. So this would be maybe the first few hours, the first day of the universe, if the universe was a year long. So this is about 400,000 years after the Big Bang, which is almost 13.8 billion years ago. So that's a long distance, long time ago. And the idea is that we can use radio telescopes to analyze a signal from hydrogen atoms in the beginning of the universe. And that way we can sort of understand how it was structured and how the first stars may have began forming. And right now we can see some of the hydrogen emissions that we're looking for, but not clearly enough. So my goal was to improve the image quality. So to understand what I was doing, you need to know how the universe evolved. So here we can see this point here is where the Big Bang was. And then you can see how it was expanding after this. This is not to scale. So right here, this black part, the dark ages, actually starts much earlier than it looks like on the chart. But the dark ages are what I'm concerned about because no one really knows much about what happened during the dark ages. We know that there was a very large amount of hydrogen atoms, very densely packed as opposed to how the universe is today. And because of that, there's no easily visible radiation. So in order to understand what was going on, you need to somehow look at the hydrogen atoms themselves. And there is a way to observe how the hydrogen atoms are structured. But it's not very easy to see. So the emission line we're looking at, the light that we're trying to observe on Earth today, comes from a hydrogen spin transition. So any sort of light you see emitted from an atom would typically come from a change in energy level. So here we have a proton, and then all of these different circles are different orbits for an electron. So it's not to scale, but the electron can only be in these particular orbits. It's quantized, it's discrete. So you can't just have an electron in your atom anywhere, it has to be in a certain location. And when it changes location, say from n equals 4 to n equals 3, it changes in the amount of energy it has. And when it changes in energy, it has to release the energy somehow. The energy has to go somewhere. So it's emitted in the form of a photon. So it's an observable photon of light with a wavelength that we can measure and we can calculate. Now, these are not the only possibilities for hydrogen. There are far more options than you would initially think. So if we look at this chart, we can see that these structures are just standard energy levels that I'm sure many of you have heard of. And then as you move to the right, these energies actually split up into other different energy levels. So in this column we have fine structure splitting, which involves the magnetic moment of an electron interacting with the magnetic field of the atom. So in this case we're looking, the angular momentum of the electron interacting with the magnetic field of the atom created by the electron. So electrons and protons act a lot like magnets. They're magnetic dipoles, so because they're electrically charged, they will interact with the magnetic field and they're moving. So even beyond the fine structure splitting, we have hyperfine structure splitting, which is when the magnetic moment of the nucleus begins to interact with the magnetic field of the electron. So this is something that is much more difficult to observe and happens much less often. So it's also a much lower energy process. So these fine structure transitions are order of maybe 10,000 times less energy than these transitions. And then the hyperfine structure splitting is even lower energy at 1/10,000th the energy. And it's also very rare. So here we have the transition probability is about 3 times 10 to the minus 15 per second. So that means if you have a single hydrogen atom, this transition that we're trying to observe only happens once every 10 million years, which is why it's very difficult to observe in a laboratory on Earth. So if we want to measure these photons that are being emitted by hydrogen atoms, then we need to have a very large number of hydrogen atoms. And thankfully this works because in the cosmic dark ages, the universe had plenty of hydrogen atoms. It was very densely packed enough that you couldn't observe photons coming through the universe very easily. So this happens enough that we can actually measure. And the reason that the energy level transition that we're measuring actually comes about because of the spin of the atoms. So the spin of a proton and the spin of an electron are just sort of an innate property of the particle where they can be either spin up or spin down. It's related to the angular momentum of the atom, of the particular particle. But in this case, they can either be in a state where they're aligned with each other in parallel or if they're anti-parallel. And the diagram we have here, which is not to scale, we have a proton and an electron. In this case, they have parallel spin. But on the rare occasion that the electron will randomly switch into, so they have an anti-parallel spin, there's a very low energy photon release. And that's an example of hyperfine structure splitting. So, in other words, we're just trying to measure this very low energy photon that is very rarely released from a hydrogen atom 13 billion light years away. And thankfully there's plenty of hydrogen so we can actually observe it. And so the reason that we're looking at this with radio telescopes, so the photon that's emitted is roughly 21 centimeters in wavelength. So it's low energy compared to light, but very high energy compared to radio waves. So the reason that we see it as a radio wave is something called redshift, cosmological redshift in this case. So if you can think of the universe as a balloon. So this would be the universe billions of years ago. You can see a wave moving across the surface of the balloon. But over time, we know that the universe is expanding. We know that space itself is expanding and objects are becoming further apart without moving relative to space. Space itself is getting bigger. So we can see that on the larger balloon, the wave is stretched down. So it's almost like if you take a slinky and you pull it apart, you'll see how it just gets stretched down to a longer wavelength and lower frequency. Because this happened over the course of 13 billion years, we have a dramatic change in wavelength from about 21 centimeters to 2 meters, which is a very large change. And the frequency after the redshift, as we observe it today, is between 10 and 200 megahertz, depending on where in the dark ages we're looking. That happens to be in the radio spectrum, so there's a significant amount of interference with what's going on with radio communications on Earth, which is why there's so much noise and why we need to put our telescope arrays in the middle of the desert. And so how do we observe these radio waves? How do we see what they're doing or get any information from them? We have radio antennas. And in this case, we have a radio telescope array. So this right here would be, you could call this a station or an antenna or a radio telescope. They're all the same thing. And you can see how it has different orientations, multiple polarizations. That way we can find information about light in different directions, different polarizations of radio waves. So we get more information per station. And this one in particular has 64 stations. It's called LIDA. And right now it's set up in New Mexico. Over the past 2 years, it's been in development. And there have been measurements made with it with 12 stations, but it's still under construction. This right here is also LIDA, and this is how we expect it to be with 256 stations. Ultimately, it will have 512 stations, which is significantly more data. The reason that we want so many of these antennas is that the more radio telescopes we have, the more information we can get, the better quality our image will be. So if you only have one antenna, you only know about one tiny location on Earth where you're collecting data. It's like having a very, very, very small camera sensor, for example. But if we have more than one, we can collect information in multiple different locations. And we can combine all of the information together into a single detailed image. So if we have two of these antennas and they're a certain distance apart, we can get a little bit more resolution, but we lose quality because we have all this empty space between them. So the ideal situation would be having the ground completely covered in a very large number of radio telescope stations. So here we have an example. This is scheduled for construction in 2020, and it would have 10,000 stations, which is 2 orders of magnitude greater than what we have now. And that would provide much more detailed, accurate, high-quality data for constructing an image of the sky. But here we have to find a way to combine all this information from all these different telescopes. It doesn't just, you can't just map it all together and have it work. It doesn't work that way. You have to take into account all these different effects from having telescopes in different locations. So here we have B and A are separate radio telescope stations, or separate antennas, and they're collecting information from a star, from a quasar, or from the 21 centimeter line, for example. And here we have a wavefront arriving, and you can see that it reaches one of them before the other. So the data isn't necessarily lined up. And because it's not lined up, we need to find a way to line it up, to build an image. And we can also gather more information knowing that these two signals are going to be out of phase. We can get more information from them. And the way that we combine this, the way that we combine these different signals is a process called cross-correlation. So if you look here, we have a graph of 2 different sine waves, and this is a movie, I'm going to play it, but watch as the red sine wave moves across the blue sine wave. And down here, you'll see the correlation coefficient, which you can calculate from the cross-correlation. So if these are lined up, you should have a correlation coefficient of 1. If they're completely out of sync with each other, you'll have a correlation coefficient of 0. So you can watch how the graph changes. It's hard to see, but you can see how the line moves up to the top and then goes back down to 0 as it moves across. So this is our main analytical technique for getting information about the sky. So, but we can't just cross-correlate two different stations. We have to do this with all of the different telescope stations, every different antenna. So we have to do a little bit of math to make all the calculations easier. What we're ultimately looking for is called a cross-power spectrum, which gives us the power, it gives us the information about the power in the frequency domain. So we can see the power in different locations of power in the sense of, I guess you would say it's the power density in the frequency domain. So we're trying to look at how power is distributed coming from these photons. So we want to see which photons have more energy. We're trying to see how they're allocated. So we ultimately want to take the Fourier transform of time series data per station cross-correlated together. But this would require us having all of the time series before we do the Fourier transform. The cross-correlator will work in real time, so we can't do this. But we can take advantage of some mathematical tricks to do the Fourier transform first. So we have this theorem here, which is an analog to the convolution theorem. It's a similar process. And it lets us transform our data from being a time series into a frequency series before we do the cross-correlation. So we ultimately come down with this matrix. Sij is just one element of the matrix. We come up with something called a correlation matrix by doing this information for all of our separate telescopes, across all frequencies, across every time sample. So there are quite a few calculations. And once we have this correlation matrix, we can build a map of the sky. So this is an image taken on LIDA, the array that I showed you earlier, with only 12 stations actively recording. This is around 70 megahertz, 50 to 75 megahertz, and it was taken over 5 minutes. Right here is the radio galaxy Cygnus A. We call it a radio galaxy because it's far enough away that the redshift will provide us with radio waves to collect using radio astronomy techniques. And we ultimately want to make this image higher quality, more detailed. We want to reach a larger portion of the sky. There are lots of ways to improve it. So there needs to be some sort of technique for improving it, which would be using more stations. Now, the problem with using more stations is that we run into a computational problem. So this graph shows you the computational intensity on the y-axis in floating point operations per second versus the number of stations. Now, both of these are log scale, but they're different log scales. So if you plotted this directly, you would just have a quadratic function. So with n stations, that scales to n squared calculations. So if we multiply the number of stations by 2, we multiply the number of calculations by 4. So as you increase the number of stations, you dramatically increase the amount of computations you need to do. So if we eventually develop this telescope array consisting of 10,000 stations, that would require 10,000 squared calculations, which is far more than we could reasonably do right now in real time. So we need tools, we need hardware tools that can actually do this math as fast as we need to do it. And there are 3 main different ways that this is traditionally done. Historically, something called ASICs have been used, which are application-specific integrated circuits. By the name, you can tell that they are specific to your application. You've designed the circuit, and it cannot be changed afterward. So you design a circuit to do whatever computations you need, send your design to a manufacturer. They would print off however many you need, and then as soon as you're done with it, you dispose of them. They're useless. So to fix that problem, FPGAs were developed, which are able to do everything ASICs do, but they can be reprogrammed in the field, hence field programmable gate array. They're also very difficult to program, so they're not ideal, but they do allow some reuse, so you don't need to buy new equipment every time. But they're also very expensive financially. But what's starting to gain traction in radio astronomy is GPUs, graphics processing units. So if you've ever played a computer game or done anything with a computer that uses a screen, you need a graphics card. This is an example of a consumer graphics card that you can buy at any electronics store, install on your computer, and play games with. That's all it is. This is the part of your computer that renders images on the screen. Your computer can do all kinds of things, but you're not going to know what's going on unless you can display it on screen, and that's where the graphics card comes in. So these are fairly cheap compared to FPGAs, and they actually allow lots of computational options for doing general math. So instead of displaying graphics on a screen, in recent years they've come to the point where you can write general purpose code that will run on a GPU. You can compile software that will use the GPU to do math. And this is new within the past few years, but it's becoming very increasingly important in science. So what makes a GPU so much better than using just a regular computer processor or CPU? GPUs can run hundreds of parallel computations. So for that, you need to know what parallel processing is. Imagine you're working in just any sort of scientific lab. You're working in a biology lab or a chemistry lab. You have a project you have to do. You have to make some measurements on a sample, take data, etc. You have options. You can either have one person do everything, one person who's fast at what they're doing, do all of the experiment itself, or you can bring 2 or 3 more people involved. Let's say you have 3 people involved. One person could prepare the sample, another person could figure out how you're going to collect data, just get that all figured out so they can just plug their data in and do analysis. And you can have another person setting up your equipment. If you have 3 people working on the project at once, you can theoretically be done in 1/3 the time. That's a dramatic speed up. That's significantly faster than if you just had one person do everything in order. That's the principle of parallel processing. If you can break up a problem into smaller, independently managed components, then you can do all of those simultaneously and piece it together in the end. So this is an example of what parallel processing is. So each one of these little lines is called a thread. And each thread would be, for example, the particular person working in the lab. So if you have 3 people working, not everything will be done as soon as the last person finishes. You're all working together, and as soon as everyone finishes, you're done with the process. You can see how that would be faster than a single person doing one thread, which is one part of the problem, then moving on to the next part, and then the next part. If you can do it all simultaneously, it's much more efficient. But you also run into a problem. What if you have 100 people working on a simple experiment that you can only break up into 3 parts? That doesn't really make sense. It would just be a significant amount of wasted time and energy. And that's where this chart comes into play. If you can parallelize a certain amount of your problem, then you get all these different lines based on how much you can do. So to start at the bottom, let's say that you can only have one person working on the experiment. Then you don't get any speed up at all. Y-axis is the speed up, and x-axis is the number of processors, number of people working on the problem, number of threads, whatever you want to call it. So here we have, if you have a problem that is 50% parallelizable, so if you can break it up into 2 parts, then right here you can see that with 2 people, you get almost a 2-person speed up. You don't get a full 2 times speed up because there's overhead, you have to organize. There's more going on than just breaking it up into 2 parts. You have to have someone actually break it up and put it back together. But as you increase the number of people, you reach a limit where it's not going to go above 2. On the other hand, if you have 75% parallel for your problem, then you can get nearly 4 times the speed up. If you have a problem that you can parallelize 95% of it, that means that 95% of the work you can break up into different people, then you can get nearly a 20 times speed up, which is certainly significant over doing all of these computations on a single thread. But you also see that as soon as you go above maybe 1,024 people for this 95% speed up, it's not really useful to increase the number of people. And this is what a GPU excels at. Newer NVIDIA GPUs can do 1,024 different calculations at once, which is nearly perfect for a 95% parallelizable problem. And that's approximately where cross-correlation is. So the problem that we're trying to solve is almost a perfect fit for GPUs. So this is what a GPU looks like. It seems really complicated, and it is very complicated. Here we have off-chip, which is the main computer, on-chip is the graphics card. You don't need to understand what all of the graph is, but you can see we have different layers of memory. As you move further down the chart, you have lower level memory. And here we have each box here, you can think of as a thread or a person doing the experiment. And then you have a group of threads here, a group here, and another group here. So groups can work together, and you can have threads working independently. Now, the reason this is all important is because we have different amounts of memory. So at the very lowest level, each thread can store data in memory, but it's a very small amount of memory, and it's a very small amount of threads that can access it. So all of these different threads, all these different workers, these different lab workers have to communicate somehow. They communicate through memory. But the more people you have communicating, the slower the communication will be. The more threads you have accessing memory, the slower they will be able to access it. So if you can break it up so they're only accessing their own memory, then they will run much faster than if they're constantly reaching further up the diagram to memory that everyone can access. So it becomes very important to specify where in memory your data is sitting. And it becomes very complicated to program. Because here we have 1, 2, 3, 4, 5, 6, 7 different layers of memory. And there's actually more if you really go into how the registers work. But it's not easy, it's not as easy to program for a GPU as it is for a CPU, where you need to specify where everything goes, what thread does what work. It's just a completely different paradigm. And it happens to fit perfectly with cross-correlation. Because if you think about the way the correlation algorithm works, you're essentially multiplying a large number of numbers by every other number. It comes down to a very large matrix multiplication. And in that case, all of the different smaller multiplications, they don't care what the other multiplications are doing. Every single number has nothing to do with every other number. They're all completely independent, which means that every multiplication can be handled by a different thread. They don't need communication. And that's why this is such an easy problem to break up into threads. And this particular program that I've been working on has record GPU usage of 79%. That means that the GPU, so all of these processors, are 80% of the time doing a calculation, which is unbelievable for a GPU. Previous to this particular program, the same program had been written by other groups running at 20 to 30% efficiency. And the theoretical limit for a GPU is around 90%. So 80% is almost as good as it gets. And that's due to very careful allocation of memory. So how do we make that even faster? There are ways to get above that 79%. Right now, in the Harvard X engine, it's called the cross-correlator I was working on, it was actually computationally bound, meaning that the computations would take a certain amount of time, and then we would have to push the data through memory. And you run into all these strange bottlenecks, where if we switch into a different multiplication algorithm, we can shift where the bottleneck is, and we can sort of bypass the bottleneck. So this all comes down to a very simple technique, Gauss's complex multiplication algorithm. So we're dealing with complex numbers coming from the radio telescope stations. And typically, you would have A plus IB times C plus ID, and then you would use this formula to calculate the product. And that involves 1, 2, 3, 4 separate multiplications. Multiplications are extremely expensive in computing time compared to an addition. And addition is almost free. And in particular on GPUs, they have something called a multiply-add operator, which runs at the same speed as a multiply operation. So additions are irrelevant. All we care about is multiplications. Now Gauss came up with this algorithm for doing complex multiplication that only requires 3 multiplications. So we're breaking the problem down from multiplying 4 numbers, from doing 4 separate multiplications into 3 multiplications. So here we calculate these 3 prefactors. Each one requires only a single multiplication, and then we add or subtract them to get our solution. it will use more bandwidth because we have to pass more data through the program. We have to worry a little bit more about our memory management. But on the other hand, we're actually doing fewer calculations. So in theory, this should speed up the algorithm. So the implementation was completed last August, and there are two different methods of doing this. Full calculation in local memory, and partial calculation in shared memory. So that goes back to this diagram here. So if you think about Gauss's algorithm, back here, we have these K1, K2, and K3. These are the prefactors. These are difficult to multiply. They're much more difficult to do than just a simple addition. And they're broken up into one multiplication and one addition per prefactor. So for the two different implementations, one method will have each individual thread do the entire complex multiplication for their numbers, which is all in local memory. So they're only accessing memory that only they can access, which is much more efficient than if they had to reach up to a higher level memory. The other way of doing this is a partial calculation in shared memory, which means that it does reach up into shared memory for a little bit of the data. So we're not sure which route will be faster. It depends on where bottlenecks show up. The full calculation in local memory will be faster if our bottleneck is bandwidth, but it will be faster to do part of it in shared memory if the bottleneck is computation, and we're not sure which one it's going to be. So the results were, we ended up having to delay testing because the hardware we wanted to test on wasn't out yet. So we ran into this problem where we ran out of memory per thread. So each thread only has a certain amount of working memory. Like if you're doing math in your head, you can only remember so many numbers at a time. Each thread or each person in the lab or each processor can only remember so much at a time. And we were running out of space. So we actually ended up making the software run slower. But there's a solution in that there are newer GPU architectures that have plenty of memory. They have more registers than we need. So we won't have to worry about running out of memory and reaching into this lower, higher level memory. And that should ultimately offer speed up. But because it's a new architecture, it requires significant optimization. But given that it can be optimized for this new architecture called Kepler, then we should be able to break the 79% limit, which would be a world record. And we should be able to get even more performance out of this cross-correlator. Ongoing research involves optimizing for Kepler in May and June. So this summer, this software will be adapted for the newer architecture, the newer graphics cards, which run on NVIDIA's Kepler architecture. And there's also a demonstration planned on the world's fastest supercomputer this summer. So the world's fastest supercomputer is now Titan, which runs, it's one of the first, it's not the first, one of the first GPU, CPU supercomputers. And right now it's classified as the fastest supercomputer. And this group at Harvard, we expect to break world records for data execution with this software, with this cross-correlator, and we plan on reaching 50 petaFLOPS, which is completely unbelievable for a supercomputer and for any sort of actual data processing problem. Theoretically, this can be achieved by just perfectly doing certain calculations, but none that actually have an application. And this would be a world record for any calculation. And there's also a plan to build LIDA 512 at Caltech in April this month. We'll start construction. It should be done at the end of the summer. And this will be the same telescope array that I showed you earlier in the pictures, but with even more stations. So we'll be able to get more data. So ultimately, by including something like Gauss's complex multiplication algorithm, which no one ever really uses anymore because it's fairly useless otherwise, we are able with that to improve the image of radio telescopes looking at what the universe looked like 13.6 billion years ago, 13.7 billion years ago. And it's amazing what this could lead to is understanding the structure of the universe, how the first stars formed. No one's sure exactly how that happened because we don't have data on what the universe out this hydrogen spectral line could potentially give us that information and lead to a much better understanding of stellar evolution, the evolution of the universe, and all other sorts of interesting phenomena. And for acknowledgements, Jonathan Cox was a postdoc at the Harvard-Smithsonian Center for Astrophysics. He helped a lot with the software. Mike Clark, an engineer at NVIDIA, he was actually a researcher at Harvard when he designed the cross-correlator that we use, the Harvard X engine, that I'm trying to optimize. He was the one who wrote it initially, and because of how well he understood CUDA, he was offered a job at NVIDIA, and he left academia. And Lincoln Greenhill is the research professor at the CFA that I worked under. I worked in his lab, and I'm grateful for that. And then Catherine Holler, John Free, and Katrina Rosenberg were all in charge of the Harvard University RE program that funded me. And I was funded by an NSF grant for undergraduate research.
Questions?
Yeah.
What was that star operation that you're doing?
Cross correlation. Let me find it. I have the definition here too. I didn't actually do any cross correlation because of this, because we were able to switch, so we were just doing a multiplication operation. But I didn't actually have to calculate it. But the definition is right here. The discrete definition is also a continuous one. And cross correlate, it's a measure of how well two different signals line up, essentially.
All right, so then the main computations you're doing or the big thing you're doing is just simultaneous multiple FFTs?
No, simultaneous multiplications. The FFT happens before the correlation. So in this formula we have here, the xi and xj, those are, this line right here is the computation that I'm doing on the GPU.
Okay.
Before that, x is just a Fourier transform of a. So a is a time series data, and then we Fourier transform it, and then we multiply those results all together.
Okay.
So essentially we're using this theorem to reorder our problem, so we're doing the Fourier transform first. And it actually comes out to being more efficient if we do it that way. Any other questions?
Now, that XIB transpose XJB?
Yes, this is...
So that's just a series of dot products?
Exactly. That's all it is. So all we're doing is calculating. We're just multiplying numbers together.
Right. Are you doing all those just by doing the dot product, or are you employing some of the better multiplication algorithms from matrices?
It's hard. We're just doing the dot product, but because of the way the GPU is set up, that's the most efficient way to do it. Because of the way the structure of the GPU works, we are just multiplying everything by everything else. And there's no real way to simplify that on a GPU. Because we're doing everything in parallel. I don't think there is anyway. It comes down to multiplying every Fourier transform time series, dotting it with every other time series. So there's no real redundancy.
Like doing all the matrix elements at one
Yeah.
time.
Yeah, and if we're doing it all at one time.
Right, but there are vastly faster multiplication algorithms for matrices.
Oh,
Yeah, but
We're
not
not
faster than
multiplying
doing
matrices.
all the elements at once.
yeah,
It's just the time it takes to do one element, because you're doing every element in parallel.
yeah.
So you're doing the whole thing at once.
Right, but for when you go to the bigger ones, right? So currently, your matrices aren't so big that you can't actually do this all at once.
Okay.
But eventually, when you get to the really big ones, there are huge parallel computations involving faster ways of multiplying two matrices. And they are you can do a bunch of these things independently.
Okay. I'm not sure how that works.
I
I
think-
don't know anything about it.
Yeah. I don't think they're worried about that large an array yet or something. So I think they can still keep it all in parallel.
I have a question.
Yeah.
So this SIGV, that's a matrix, right? It's an outer part of the Javio. The XIVT, XG, V. It's so you multiply this to end up with matrix. Is that right?
Xi and Xj are both just they're a sequence of numbers.
Right.
And we're dotting them together. We're just doing a dot product. That's why we have the transpose. So Sij is an element of a three-dimensional matrix.
Okay.
So
okay.
Sij itself.
So it's an inner product. Okay.
And it's a function of the frequency. You do it simply.
Yeah.
And then from our correlation matrix, we get our image of what the sky looks like. Any other questions?
So when do you get images out of this?
Oh, okay. So what we have here, I didn't work with that, so I don't fully understand it. But, so I'm not exactly sure what they're doing. I know they're measuring across power spectrum, which gives us the power density and the frequency domain per sample. We're integrating over a large number of samples. That's what that one is. But we're getting a power density over the frequency domain. And that's, I believe, what we're just using here.
So if you go back to the previous slide, I think that's where that is. Is that multiplication? That may be the matrix. That when you sum it over here, T colon I of XTV multiplied by XTV, maybe that's a matrix.
Yes.
Yeah, that's exactly. That's correlation matrix. Is add all them together, and if they were perfectly aligned, you get a diagonal matrix, but they're not, so you're gonna have this. Okay.
That's right. And we're not worried about this during our initial calculation. This is all done after collecting all the data.
Sure.